Welcome back to the Quick Machine tutorial series. In the last video we started talking about the transient solution, and in this video we're going to continue that discussion. So as a quick reminder, last time we saw that once you've created your model, you can come up over here and fill out this form to generate a series of static solutions in order to create your flux and your torque surfaces. So once you have these two neural networks created, all you have to do is come over here to this Run tab and click Start, and your transient solution will be started. You can actually see the motor running as it goes along, and this form right here is entirely live. So if I wanted to, let me just speed this up for a second. If I wanted to, say, apply some sort of load torque, I can give it a torque value, and you can actually watch the motor slow down. Okay. So in this lecture, video, I should say, the first thing that we're going to cover are these scripts right here. This motor control, this driver control, and you have an output script. So one of the important things to optimize when you're creating a motor is your switching, right? So when do you turn your phases on and off, and how do you apply your voltage to your phases? So by default, your motor controller script is going to do that for you. This defines exactly how your phases are turned on and off, and this is completely editable. You can come in here and edit it any way you want. Let me just zoom in here for a second. So all I did there was click Control, and I used the scroll button on the mouse, and you can zoom in and out. So the scripting language is called Lua scripting language. So it has its own website. You can look at its own documentation. I find the syntax to be pretty similar to MATLAB. If you're familiar with MATLAB, this should be similar anyway. So for instance, right here is a for loop. You have if-else statements in here. So this is a very simple script. Basically all it does is it loops through your phases. You note that you have this num phases. That is a variable that's provided to you. So that's automatically set for you. So all you have to do is use this num phases, and in this case that's going to be equivalent to 3. You then, if you look down here, there's this statement right here, this if is on. So this is on is a function that I provide. This is a function that I wrote. You basically just give it an integer, some value between 0 and num phases minus 1. And what it does is it goes in here and it looks at your winding table, and it determines, given my current angle of my rotor, is that phase on? Is that phase firing? So if it is firing, then I'm going to set the voltage for that phase to this V. This is another defined variable, and actually this V is tied to this input. So as I change this input, this V changes as well. So that's how this form gives you live updates as your motor's running. So this is just kind of a very brief introduction into how you can use these Lua scripts. If you want to come down to your Quick Machine user manual, again, all you have to do is under the Help menu, Documentation, look up the user manual. In here, in section 7.4 is a Lua scripting section. And the most important parts are right here, where it lists off all your variables that you have access to and all the functions that I've already written for you. So one really powerful thing that you have here is these 3 functions down here. So if you have MATLAB installed, you can use any one of these 3 functions. You can use this put mat, which if you create a Lua table, you can actually add that to a MATLAB environment. So that's what this put mat does. So it actually adds, you think it creates the same table inside of MATLAB. Then you can use this execute mat function. So all you do is you give it a string, like a command, any sort of MATLAB command, and you can use those variables that you've already sort of put into your MATLAB environment, and so you should be able to do anything you really want to with MATLAB. You really have full access to MATLAB with just these three functions. So the final function is getMat. So that's where you can get a matrix or a Lua table from MATLAB. And if you come down here, it's a little bit hard to see. Let me just zoom in. Okay, so here's an example of using those three functions. So I'm creating a Lua table, I'm just calling it P, and I just sort of fill out this Lua table. It's a two-dimensional table. So you notice that the first thing you have to do is set, so this is actually a table of tables. That's the proper way of thinking about it, but it really is just a matrix, and you can access the individual components like that. So once I've created this matrix, filled it with some numbers, I can say put mat p, and then I define what the variable name is for the MATLAB environment. Then you have to tell it its dimensions. So that'll add my Lua table to MATLAB. Then I can use this, I use this function here to say execute mat, and here I'm going to say p equals p times p. Right. So all I'm going to do is just square this matrix p inside of MATLAB. So once I do that, MATLAB will square p for me, and now all I have to do is get p back from the MATLAB environment. So there's lots of different options that you can do in order to set your phases. But the main point of this motor control script is that you have to set this voltage vector. You have to set the voltage for each one of your phases. So how you do that is entirely up to you. But the most important thing is you have to set this voltage vector. So one other thing that you might want to do is you might want to run more elaborate tests than just to run this simulator and play around with it. Simulator is nice to give you sort of instant feedback on what's going on, but if you really want to run an elaborate test, say you want to create a speed torque efficiency curve or efficiency surface. And so one of the things you might want to do is you might want to iterate over a bunch of different voltages, and for each one of your voltages you want to slowly ramp up your load torque until your motor essentially stalls or starts running backwards, and just collect data as you go along. That's exactly what this driver control script does by default. So you can think of this driver control script as acting as a dyno, right? This is what's testing your motor. And in order to run this driver control script, if you go down to run and you hit this run script button, this will run this script. Okay, so there's a lot going on in this script, but it basically does exactly what I just said. It ramps, or it runs through a bunch of different voltage values, and you can kind of define here what your voltage values are in these variables here. For instance, this is a volt increment, so this tells the script as I'm running through these voltages, I want to start at the initial voltage defined here, and I'm just going to use this voltage increment to just step through a series of voltages, and then for each one of those I'm going to ramp my torque from the initial value here, whatever I have here, this is going to be the initial value for my torque, and I'm going to ramp my torque using this torque increment. And I'm going to continue ramping until my motor stalls out or starts running backwards, something like that. So one thing to note too is once you set your current, or sorry, once you've set your voltage and you've set your load torque, you need to give the motor time to settle down, to hit an equilibrium. So there's this variable in here called settle time, and that will tell your script how long to wait for your motor to hit your equilibrium. And then you have your start output time, and this is where you actually start collecting data. So in this case, you're going to so your total time here is going to be the settle time at 0.5 seconds, and this is actual simulation, or I should say, it's the time with respect to your simulation. This isn't actual how much time has passed in the real world. This is the number of time steps needed to execute a half a second of the simulation. So that's what these times are talking about. So the way this is set up is, I guess, it's a little bit confusing because the settle time is so it's going to sit there and wait for half a second before it starts ramping your torque another increment, and 0.3 seconds into that half a second is actually going to start recording data. So the amount of time that records data in this situation is 0.2 seconds. Now you have to be careful with the way you set these two variables, because you don't want to actually record too much data. You could very easily record too much data to the point that you're having 16 gigabyte files, something like that. Okay, so first I should also mention that everything that's kind of blocked off in these weird looking brackets, that means that this whole paragraph is a comment and it's not actually involved in execution. Same thing, anything that has these two little dashes in front of it, that is also a comment. So if you're curious exactly how this script works, it's pretty well commented. I made sure to add tons of comments so that you can use this script, work from it, create your own sort of tests, and really do whatever you can imagine, whatever types of tests you can imagine. So one other thing, before you hit this run script button, what you want to do is you want to uncheck this pick. So if I start my simulation, you can see these numbers changing here, but the picture on the side stays the same, right? If I check the pick, then the picture updates, which really slows down the computation, right? If you're running a really long, elaborate tests, you don't actually want your picture to update. So another thing you can see here is you have this debug screen, and the way that works, so first of all, notice that it just sort of appeared after I click start. It'll appear too if you click the run script. And what that does is that gives you an opportunity to debug these scripts. So at any point in your script, you can use the command print debug and give it a string, and that string will be written to this debug form here. So it gives you a nice way of checking whether or not your script's actually doing what you think it's doing. Okay, so this final script here is this output script. So as I said before, in this driver control script, the way it works is you have this settle time and you have this start output time. So after the start output time, you start collecting data. So what data you actually collect is determined by this script. The same thing happens when you click this record button. if you're just running this basic simulator. This script will execute at every time step and collect whatever data you want. So again, if you're curious about what is being outputted and how it's being computed, please look at this script. It's pretty well documented again, so it should be pretty easy to follow. And if you want other things to be outputted, just do that here in this script. Alright, so one thing is I'm going to talk about now. So again, there's two modes that you can have to your simulation, right? You can look at a fixed torque or a fixed speed. So right now I'm running in fixed torque mode, and so my speed is allowed to vary depending upon when it hits an equilibrium with respect to your voltage. So as you increase your voltage, your speed should increase as well. So let's change this to a fixed speed mode, and so I can come in here and set my speed to 1500 RPMs, so something like that. So now I'm running at 1500 RPMs, and one thing to notice is if you look at your load torque, you can see it go up and down in order to maintain that 1500 RPMs. So one thing I'm going to do is just collect some data. So I just hit that record button, and so if you remember right here before this debug script got put up, there was that output file input, and that's where you define where all your data is written, in what file. So okay, so I've recorded quite a bit of data. I'll just hit this end button, and what pops up is a graph form, or a form that helps you analyze the data that we've just collected. So again, here's my output file. If you look at that output file, it's going to be this file right here. So the first thing to notice is that I can actually add other files to this table and collect even more data. And this will be helpful if your simulation is stored over multiple files. So all you'd have to do to add another file is click this add file or add folder. This absolute value means that if you click that absolute value, then everything that's a negative is turned to a positive in your file. So don't worry about what this combine and sort section of this form does. We'll talk about that here in a little bit. That's more for three-dimensional data. So one thing you might want to do is you might want to filter your data. So all you have to do is come over here, and these columns or these columns of data are entirely defined by what you do in your output script. So one of the things I can do is I can filter on my efficiency, and I can say I only want to look at efficiency that's less than 100%. Anything greater than 100%, I know is not valid. You can even do that. So I'm just going to delete any row that's over 100% efficiency. So if I do that and you click apply a filter, say okay, filter, file is filtered. Another thing you can do is you can say, oh, let's look at my phase is 0, and I only want to look at data where my phase 0 is increasing. My phase 0 current, I should say. So what that'll do is that'll pick out the first point in your data, and it'll start adding rows as long as those rows increase your phase 0 current. Anything that starts decreasing your phase 0 current will just basically drop those rows. So I'm not going to apply this filter because it really doesn't make sense in this case. But at any time, after any filters that you apply, if you want to check to make sure your filter does what you think it should, you just click this export data button, and as long as you have Microsoft Excel, this will pop up and Excel and you can look at your data. Alright, so here's the data that we collected. And again, you can do this at any time. It's very useful if you don't really know exactly what these filters are doing. Play around with it, export the data, and just make sure it's doing what you think it's doing. Alright, so now let's go ahead and create a two-dimensional plot. So if you hit this 2D plot button, you can now define a 2D graph. So all you have to do is tell it your x-axis and what your y-axis is going to be. Okay, so I'm going to look at your phase zero current with respect to time. Now the way this form is set up is it allows you to add multiple 2D plots per figure. So I can add that graph, and now I can add other 2D plots. So for instance, if I really just want to look at phase zero, how phase zero is working, I can plot the current, the voltage, the torque. So one thing right now, this plot is going to have a blue color with a solid line. Maybe I want to change my voltage plot, make it red with a dashed line. And I can come down here and maybe I want to look at torque that's produced by my phase zero. And come in here and say, okay, maybe I want a green line and I want it dotted. So I add that graph. Now if I click this view button, you'll see the MATLAB figure will pop up. And it gives you a nice view of those three graphs that I told it to make. Let me just make this a little bit bigger. So as you can see, it created this is your graph of your current, here's the graph of your voltage, and down here in this very light green shows the torque produced by your phase. Okay, so that pretty much covers what you can do with a 2D plot. One helpful thing would be to create a nice 3D surface, especially if you're running, say, this driver control script and you want to create a speed, torque, and efficiency plot. So another way you can open up this graph form is if you click Open Graph. Now I can come down here and select any sort of data file that I have collected. So I'll just open up this one. Give it a second. Okay. So this is a data file that we collected using that driver control script. So one of the things you want to do now is remember your driver control script by default. What it's going to do is it's going to set a voltage level and then a load torque, and then it's going to collect a bunch of data. And what we really want to do is we want to combine all of that data that was collected for a specific voltage and a specific load torque into a single point. So let's just look at the data. So real quick, I'll just export my data, and this will open it up into Excel. Okay, so here's the data that I actually collected. So in this case, I started out at 5 volts and my load torque's at 0.1 Newton meters. You can see I'm collecting all of these data points, and I want to combine all of these points, or all of these rows, into a single point. So if you come down here, see now I switched to a new point. So here I've gone from, so I want to combine these first 1,000 rows into a single point. So the way you're going to do that is, oops, let me get rid of this. So the way you're going to do that is you're going to say, I want to look at my voltage, and I'm going to create this grid. And everything that falls inside a square on my grid is going to be combined into a single point. So here I'm going to set my x-axis, and I'm going to look at my voltage. Right? That's going to define my first part of my grid. And I'm going to have an increments of 1, because that's the way I incremented my voltage in the driver control script. Now, I don't want my grid to be from 0 to 1 on voltage. I actually want it to be kind of in between that. So I want it to be from 0.5 to 1.5. That's going to define my nice little box for one of my squares. I'm going to do the same thing for my load torque. Right? My load torque had an increment of 0.1. And so I'm going to make my offset 0.05. Normally make your offset about half of what your increment is. Right? That's going to basically shift your grid over just a little bit and to sort of center it on these points. So now, as you saw before, right? So my first point for my voltage was 5 value with 0.1 Newton meters of torque, and there's a ton of rows of data. But all of those rows of data are going to fit in a single square on my grid with respect to the voltage and the load torque. And I want to combine all of those rows into a single point. And so there's 2 ways that you can actually combine them now. You can say I want to choose a specific row. So I want to say maybe I want to look at my efficiency, and I want to find the row that has my max efficiency, or my minimum, or the average efficiency. Or I can even say something that says something like I want to find the efficiency that's closest to 75%. You can do that. Or you can come up here and say I want to combine the rows here, and this tells you how you combine each. So you're going to combine each column independently of all your sets of rows. So here I can say that I want to take the average time, the average speed, average voltage. You can change any one of these to say I want to take the max speed, the min speed, anything like that. So you can actually choose your how each individual column is combined with your sets of rows. So once you have this all set up, click this combine and sort. So the combine and sort is finished, and now click export data. So now, if we look at our data now, so I start at 5 volts, first point is at 0.1 Newton meters. Look at the next point. It's at 0.2, 0.3, 0.4. It has nice increments. So if I come down here, now look that once I've reached about 2.1 Newton meters, I've basically stalled out the motor here, so I'm going to increment my voltage to 6 and continue on with my data collecting. So this gives you a nice way of just sorting out your data and combining it into these nice little squares so that you can make nice plots. Okay. Alright, so I've actually just loaded up a different data file because I didn't like the way that graph looked. I didn't like the way the graph looked for that previous file. I didn't run the test long enough to actually get proper data and to get a proper 3D graph. So I've changed this file, and this is a file that we've collected from an actual dyno. And this is just to show you how the 3D plot works and to give you a nice view of all the options that you have for it. So once again you've combined and sorted your data, click the 3D plot view. And so now all you have to do here is tell it what your x-axis, your y-axis, and your z-axis. So here I want to look at speed, torque, and efficiency. And if I click view, you get a nice 3D graph. Right. So now, first of all, notice that the graph is kind of noisy. If you want to smooth that out a bit, you can use this Gaussian blur to help smooth it out. So the first thing you have to do with a Gaussian blur is you have to say, I want to interpolate the data. And this slider here tells you how fine the interpolation is. So if I move it to the right, it's going to be a more continuous interpolation. If I move it to the left, it's going to be more discrete. Warning, if you move it all the way to the right, it's going to take a long time to compute if you have a lot of data. So I usually keep it somewhere in the middle. And you click the view again. And you can see that the plot has already started to sort of smooth out a little bit. It looks a little bit more continuous, not as jumpy and discrete. So now, if you click, say, I want to do a Gaussian blur, so you tell it how many iterations of a Gaussian blur you want to do. So in this case, you can either do 2D or 3D. The 2D will basically takes a weighted average of the neighboring cells. So I click view on that. Alright, so now you can really see it's starting to smooth it out a little bit. Far less jumpy. And so if I increase the number of iterations, right, the smoother it's going to get. But then again, the less accurate your data is going to be. So here. So another thing you can do instead of looking at a surface plot is you can look at contours. So here's a nice contour plot of your data, and you can actually specify what contours you want. Maybe I want it at 10, and this is on your z-axis, so 10% efficiency, 37% efficient, or 27% efficiency, and so on. Or you can delete these. So that basically, I think, covers it as far as what you can do with a 3D graph. We're using this quick machine form. So go ahead and close out of this, close out of that, and I think that just about covers all of the functionality with respect to the transient solution. So thanks again for watching. A big thank you to the people at Dakota Power for helping me develop this program. It was a significant effort to make this program work. So thanks for everybody for using it, and happy modeling.